So we have seen that a problem or a DFA where we constructed the DFA for set of all strings of length exactly 2. Now what if the question is construct a DFA which accepts set of all strings over a comma b where the string length is at least 2. Now I want to construct a DFA for set of all strings over a comma b, DFA for set of all strings over a comma b such that length of the string is at least 2, greater than or equal to 2. So how can we construct it? First of all, identify the sigma. Sigma is nothing but a comma b. And now we have to identify the words, the language. Language contains set of all strings of length greater than or equal to 2. So strings of length 2, AA, AB, BA, BB, and strings of length 3, AAA, so on, BBB, so on. Finite or infinite? Definitely the language is infinite. If a language is finite, we will be able to give finite automata. But if the language is infinite, we don't know whether we will be able to give finite automata or not. But then we shall try. We shall try to give a finite automata for this. So as usual, take the smallest string and give the skeleton and then try to understand the states. This is in the language, so I am accepting it. Now try to understand the states. What does this state represent? This state represents set of all strings of length 0. What does this state represent? This state represents set of all strings of length 1, set of all strings of length 2. If I see small a or small b, it makes they are all these strings of length 1. Then if I see a followed by a or a b followed by a and a followed by b or b followed by b, all these are set of all strings of length 2. So according to the question, I had even accept set of all strings of length 2 and I have accepted set of all strings of length 2 here because this is the final state. Now is this a DFA? No, it is not the DFA. The reason is for state A and state B we have shown the transitions on small a small b, but for state small c we didn't show any transition. For the state C we didn't show any transition. How? So we have to decide about what happens if I see one more a or b. Already we have seen a string of length 2 and we have reached C, and now if you see one more a or b, that is nothing but strings of length greater than or equal to 2. Therefore I am going to accept it. Why? Because all the strings which are greater than or equal to 2 have to be accepted. So if you look at this, we have 3 states and the C is the final state, and C even represents set of all strings of length 2 or more. 2 is because of these 2 transitions and more is because of this one. Now let's see the problem where we want to design a DFA which accepts set of all strings over a comma b such that length of the string is less than or equal to 2. We have seen exactly equal to 2, we have seen at least 2, now it is at most 2. This is at most 2. Okay, so what does this contain? This contains set of all strings of length 0 because 0 is less than 2, of length 1 and of length 2. So if I enumerate the language is going to be set of all strings of length 0 which is sigma and epsilon, and set of all strings of length 1 which is a comma b, and set of all strings of length 2 which is AA, AB, BA, BB. What can you say about the language? It is finite. Since the language is finite, we will definitely be able to give finite automata. So whenever the language is finite, obviously you have to give the skeleton taking the biggest string. So I am going to do like this. I'll be giving for this a, accept it. Okay, now let's talk about the relevance of these states according to this problem. Now the first state, let's call it A, represents set of all strings of length 0, and the second state, this one let us call B, represents set of all strings of length 1. C represents set of all strings of length 2. I can write like this. Why? Because A or B is set of all strings of length 1 and followed by A or B is nothing but set of all strings of length 2. So whatever we wanted to accept, we have to accept epsilon. Always remember, whenever we have to accept epsilon in a DFA, make initial state equal to final state. There is no other way we can accept a epsilon in a DFA other than this. Therefore, always make this one as final state, and we have to even accept A or B. Therefore, I have to make this one also final. So 0 length, 1 length, 2 length. Is this the DFA? Final answer? I think it is not the DFA. Why? Because A and B are complete, but for C we didn't give any transition on A or B. So just think about what will happen if I see small a or small b at state C. This will lead to any string of length 3, and we should not accept it because maximum length that is accepted is 3. So this is nothing but set of all strings of length 3 and more. Because of this loop, 3 or more, and this is going to act as a dead state, because once I reach this state D, there is no way I can again come back and reach any of the final states. Therefore the D is dead state. So this is the minimal finite automata. Okay, so whenever I was discussing about DFAs, keep one thing in mind. I was drawing everything, I was designing this just with practice. When you try to do the same, when you try to construct the DFAs on your own, you might get some other answer, and that answer might be right. So given a language, you can draw many DFAs. A language may contain many DFAs, but then it will always contain only one minimal DFA. If you draw any DFA for this language using minimum number of states, which is 4, you should always get this. You can even construct a DFA which will have more states and which is also right, but then I am interested in minimal DFAs. There is a procedure to construct a DFA, a correct DFA, and then minimize it into this, but then try drawing the DFA as minimal as possible, because it will help you in the exam. Till now we have seen 3 kinds of problems. One is string length is exactly 2. The string length is exactly 2, and the other is string length is at least 2, and the other is string length is at most 2. So let's just see the diagrams. String length is exactly 2. A or B, I'll accept it, and if I get anything else, I'm going to reject it. String length is at least 2. A or B, I'll accept it, and anything I'll accept it. Next one, string length is at most 2. A or B, B, 0 length string, 1 length string, 2 length string, and A or B. I'll reject it. So now if you look at this, the number of states in the string of length 2 is 4, and in the string of length greater than or equal to 2 is 3, less than or equal to 2 is 4. So why do you think that we need 2 states here? 4 states here. 3 states are required to put the string of length 2 onto it. These 3 states are definitely required, and then 1 state is required because I don't want to accept anything greater than 2. Here 3 states are required because 2 states are used to put the string of length 2, and then the third state is just going to accept anything. and here also 3 states are required to accept strings of length 2, and then one more state is used to just to not to accept anything greater than 2. Therefore, in general, if I have to accept strings of length n, then the number of states required is n plus 2. Number of states required in a minimal DFA which accepts set of all strings whose length is n plus 2. Now number of states required in a minimal DFA which accepts set of all strings whose length is greater than or equal to n, which means whose length is at least n is n plus 1 and whose length is at most n is n plus 2. This is an important point. You please try to remember this because it is a frequently asked gate question. Okay. Now, let us say we want to construct a minimal DFA which accepts set of all strings over a comma b. W is a string over a comma b such that if I take the length of W and if I divide it with 2, if I take length of W and if I divide it with 2, then the remainder should be 0. So what does this mean? It means that if I take a string whose length is, if I take the length of a string and if I divide it with 2, the remainder should be 0, which is nothing but the length of the string should be even. If I take any even length string and if I divide the length of it by 2, definitely the remainder is going to be 0. If I take any odd length string, it is going to be 1. So how should I start it is, let's write down the language. What does the language contain? Language will definitely contain set of all strings of length 0, which is nothing but epsilon, and set of all strings of length 2. So what are all the strings of length 2? AA, AB, BA, BB, and set of all strings of length 4, A, so on, B, so on. Finite or infinite? Definitely the language is infinite. Why is it infinite? Because we have lot of strings, and it is not finite because we don't have any upper bound on the length of the string. The condition is it has to be divisible by 2. So whenever the language is infinite, we don't know whether we can give finite automata or not. But then let's just try using the previous methods we have learnt. Let us say the first state indicates set of all strings of length 0. If I see A or B, it indicates set of all strings of length 1. So I have to accept set of all strings of length 0 because epsilon is there in the language, and I should not accept set of all strings of length 1 because A or B are not in the language. And then next one is, if I go to one more state on seeing A or B, this represents set of all strings of length 2 and which are there in the language, therefore I have to accept it. If I see one more A or B, it is going to be set of all strings of length 3, I should not accept it. A or B, set of all strings of length 4, I should accept it, so on. So if I use this method, the finite automata is never going to end. In fact, then it should not be called a finite automata. Why is it called a finite automata is the number of states inside the finite automata is finite. That is the reason we are calling it as finite automata. And now if you make it infinite, it is definitely not a finite automata. So let's try to decrease the number of states using some method, some intuition. See, actually I want to differentiate between two things. One is even length and other is odd length strings. I don't want to distinguish the strings between every length. I just want to distinguish it between two classes. One is even length strings and other is odd length strings. Let us see if I can do it. This is odd length, this is even length. If I get one more A or B, it is odd length. A or B 1 length, A or B 1 length, 1 length, 2 length, 3 length. If I get one more A or B, 4 length. If I get one more A or B, 5 length. If I get one more A or B, 6 length. If I get one more A or B, 7. One more A or B, 8. So on. So this is nothing but set of all strings of odd length strings, right? And this is nothing but even length strings. So this is definitely a finite automata, and this is definitely deterministic finite automata. It is finite automata because the number of states are finite, and it is deterministic finite automata because for every state we have shown what to do on small a and small b. It is definitely DFA, but then it is not minimal. The reason is I can even try to minimize it. Let us say when my purpose is to distinguish only between two classes of strings, one is class of strings whose length is even, other is class of strings whose length is odd, then I will have only two states. One state is going to accept even length strings and other state is going to accept odd length strings. Okay, so see this. This is nothing but strings of length even, strings are of length odd. Okay, so 0 length, 1 length. If I get one more a or b, this is going to be 2 length, 3 length, 4 length, 5 length, 6 length, 7 length. Therefore this is the final DFA which accepts set of all strings whose length is divisible by 2. What if I want to accept set of all strings whose length is not divisible by 2, which is set of all strings whose length when divided by 2 is 1, which means set of all odd strings. So how can I solve this problem? You can take the same one, this state, initial state indicates set of all strings of length 0, and on seeing a comma b, if you accept it, this is set of all strings of length 1. On seeing a comma b, set of all strings of length 0, of length 1, of length 2, of length 3, 4, 5, 0, 1, 2, 3, 4, 5, so on. So this will accept odd length strings, this will accept even length strings. So by looking at this problem, we can even analyze it in another way. When a number is divided by 2, we get two possible remainders. One is remainder can be 0 and the remainder can be 1. That is why I am having two states. If the question is the string length has to be divisible by 3, then we will get 3 states. Why? Because when we divide any string with a number 3, then the possible remainders are 0, 1, 2. We shall solve it in the next question. Now let us say we have to construct a DFA which accepts set of all strings over a comma b such that length of the string when divided by 3 is 1. Length of the string when divided by 3 is let us say the remainder of the length of the string when divided by 3 is 0. It is nothing but I want the length of the string to be a divisible by 3. So first thing is, let us find out the language. So language contains set of all strings of length 0. Why? Because 0 divided by 3 is 0. And set of all strings of length 3, which is a, b, so on, b. And next one is set of all strings of length 6, a, so on. Finite or infinite? Definitely the language is infinite, and so we don't know whether I will be able to give finite automata or not, but then let's try it. So first thing is, since we had to accept epsilon, initial state is going to be final state. This represents set of all strings. So before this, in order to decide about number of states, we have to think about this problem in some other way. Let us take any number and let us divide it by 3. Whenever I divide any number by 3, the possible remainders are 1 is 0, 1, 2. So if I divide any number with 3, the possible remainders are 0 or 1 or 2. Therefore we should at least have 3 states which will distinguish the remainders, right? So this is going to classify the entire strings into 3 classes. So if I don't see anything, it is nothing but string of length 0. If I see a string a or b, it is nothing but strings of length 1. If I see a or b followed by a or b, it is string of length 2. If I see one more a or b, it is nothing but string of length 3. If I have a string of length 3, then if it is divided by 0, if it is divided by 3, the remainder is going to be 0. So string of length 0, string of length 1, string of length 2, string of length 3, string of length 4, string of length 5, string of length 6, 7, 8, which means this state is going to indicate set of all strings whose length when divided by 3 is going to give a remainder of 0. This one is going to indicate set of all strings whose length when divided by 3 is going to give a remainder of 1. It is going to give a remainder of 2. So Q0, Q1, Q2. Right? What if the question is if length of this string is congruent to 1 mod 3. Length of the string is congruent to 1 mod 3. It means that if I take the length of the string and if I divide it with 3, then the remainder should be 1. In that case, Q1 is going to be final, isn't it? Instead of 0, if I have 1 here, then Q1 is going to be final. The other way of writing, this one is length of the string mod 3 equal to 1, or mod W is congruent to 1 mod 3. Both are same. Both are same. So either if the question is this or if the question is this, then Q0 is not going to be the final state, Q1 is going to be the final state. You can even extend this concept to any level. Let us say length of the string mod n equal to 0, or length of the string is congruent to some number mod n. If that is the case, then the minimal DFA for this one is going to contain n number of states. Always remember, if it is divisible by 3, then 3 number of states. If it is divisible by 4, then there is 4 number of states. In general, if it is divisible by n, then it is going to contain n number of states. You can generalize this to that extent. Done. Okay, till now we have seen the questions which were asked on the length of the strings. So you might have seen this state represents 0 length, and then this state represent 1 length, and this state represent 2 length, so on, right? And the question can even be asked on number of A's or number of B's, which means I am not interested in complete string. I can even ask only about the number of A's in a string or only about the number of B's in a string. So let's just look at one example. Let us say I want to construct a minimal DFA which accepts set of all strings over a comma b. Definitely set of all strings over a comma b where number of A's in W, if I take number of A's in W, that should be 2, which is nothing but I should contain, all these strings should contain only 2 A's, right? And any number of B's. There is no restriction on B's. So the fact that there is no restriction on B's is going to lead to infinity. The language is going to be infinite only because of the fact that there is no restriction on number of B's. So let's just write the language. What is the smallest string which is containing 2 A's? Simply 2 A's, right? And then it can contain any combination of B's along with these 2 A's. Any combination of B's along with these 2 A's. Any combination, and there can be any number of B's. But then important thing is there will be only 2 A's. Okay, so first thing is I am going to construct DFA for AA. So this is the basic skeleton AA. So once you know it is there in the language, therefore I am going to accept it. Once you construct the basic skeleton, just try to think about the relevance of these states in this finite automata. This state, what is the relevance of this state? The first state, our problem is to count the number of A's. According to the problem, the relevance of this state is, this state indicates 0 number of A's, which means I didn't see any A's, 0 A's. And what about the relevance of this one? Relevance of this one is, this state indicates 1 A, and this state indicates 2 A's. So 0 number of A's, I will be here. If I see 1 A, I will be here. If I see 2 A's, I will be here. Then is this a finite DFA? This is definitely finite automata because the number of states are finite. Is this a DFA? No, because in the state A, we have seen what to do on small a, but we didn't see what if I get a small b. Even if I get any number of b's, it is not going to add to the number of a's. Therefore, b's should be kept out of counting, which means b should not lead to any transition. Therefore, they will be kept out of counting. Okay, and this state is complete. What about this state b? You have seen on a, what if I get a b? Again the same reason, b's should never contribute to the counting. B's should never contribute to the counting, right? Okay, so is everything, is this a final, is this a DFA? This state is complete, this state is complete. What about this state C? In state C, we have seen only about B. What if I get a? That is what we have to see. So what can I do if I get a? Right? So if I get one more a, it is nothing but it is leading to 3's. If I get one more a, I will go to other state and I will remember that I have seen 3 a's till now, and that should not be accepted, and anything after that, it should not be accepted. So once I see 3 a's, I don't care whatever I get after it, I am going to reject all of them. So this is going to act as a dead state. What is a dead state? It is a state from which there is no path to the final state. Got it? So this is the basic automata which will accept all strings which are containing exactly 2 a's. Now let's say I want number of a's in W to be at least 2, which means at least I should have 2 a's. Then what do you think should be the modification? At least 2 a's is nothing but I will not have this. I know I'll be having a comma b. So if you can pass it and make a note of it, I'm going to change it. Now if I have to do number of a's is greater than or equal to 2, it is nothing but it will not contain this part, this entire part. It is going to be this, right? And what if number of a's in W should be less than or equal to 2? Then it is even going to contain all the parts, and A is going to be final and B is going to be final. The same way how we did for the string length, it is going to be same. Okay, so the string, this question can be extended to any number of varieties. Got it? Let us say we want to accept set of all strings where number of a's in the string is even. So you can think of this problem as the same one which we have seen for the string length, but the only difference is here I am interested in only number of a's. In string length I was interested in both number of a's as well as number of b's. So think about this problem. Now I want to accept set of all strings which are present in sigma equal to, see this, let us say I want to construct minimal DFA which accepts set of all strings present in a comma b such that number of a's in W mod 2 equal to 0, or I can even say number of a's in W is congruent to 0 mod 2. Meaning of this is this string should contain even number of a's. You can do it in a similar way, the same way how you did for the string length, but the only difference is counting should only involve a's, not b's. Therefore, I'll have two states. One will say even number of a's, other will say odd number of a's. If I don't see anything, it is even number of a's. If I see 1 a, it is odd number of a's. 2 a's even, 3 a's odd, 4 a's even, 5 a's odd. And what about the number of b's? B's will never contribute to counting. B's will never contribute to counting. So instead of writing like this, I will write Q odd, Q even, and this is the final state. Got it? So even you can extend this question, or you can even ask what if the number of a's is odd. If the number of a's is odd, then Q is not going to be the final state, Q naught is going to be the final state, right? You can even extend this question to what if number of a's is multiple of 3, which means you can even ask me the question, this one, number of a's in W mod 3 equal to 0, which is nothing but number of a's in W is multiple of 3. So I can write it like this. So I'll have 3 states. One state is, if I divide the number of A's, it is going to be, the remainder is going to be 0. If I divide the number of A's, the remainder is 1. If I divide the number of A's, the remainder is 2. So if the number of A's in W mod 3 is equal to 2, that means that Q naught has to be the final state. And if I see A, this is it. If I see one more A, this is it. If I see one more A, this is it. You can even check it. 0 A's, 1 A, 2 A, 3 A's divisible by 3, 4 A, 5 A's, 6 A's divisible by 3, 7A, 8A, 9 A's divisible by 3. What about B's? B's will not lead to any counting. Got it? So you can extend the question to number of B's, right? And you can extend the question to divisible by n. What if I say number of A's in W is congruent to some number, let us say k mod n. How many states do you think this one will contain? This one will contain n states, because if I divide any number with n, I'll get n remainders, 0 to n minus 1. And what is k here? Some constant, right? So what if the question is number of A's in W mod 3 equal to 1? It is going to be simply, if I put 1 here, Q1 is going to be the remainder, right? Q1 is going to be the final state. If it is 2, Q2 is going to be final state. If it is 0, 0 is going to be the final state. Okay. Till now we have seen the string length, number of A's, and now I want to have some restriction on number of A's as well as number of B's. Let us say I want to draw a minimal DFA which accepts set of all strings over A comma B in such a way that number of A's in that string is congruent to 0 mod 2 and number of B's in W is congruent to 0 mod 2, which means I want to accept set of all strings in which both number of A's as well as number of B's should be even. They should be even. So what could be the language? Is it similar to the problem of string length, or is it similar to the problem of A's, number of A's, or is it similar to the problem of number of B's? It is somewhat difficult. See this, you may say that if a string is going to contain even number of A's and even number of B's, definitely the length of the string is even. So you might think that why not give a DFA which accepts set of all strings of even length. Again, see this, you might think that if the number of A's and number of B's are going to be even, then the string length is going to be even. Therefore you might argue that why don't you give the finite automata which accepts set of all strings of even length. Okay, but then the problem with this is, see this, I can give you a even length string, but then the number of A's and number of B's may not be even. For example, see this, AB, this is a even length string, isn't it? But then number of A's and number of B's need not be even, which means if a string is containing even number of A's and even number of B's, definitely the length of the string will be, if the string is going to contain even number of A's and even number of B's, definitely the length of the string is going to be even, but the reverse is not true, which means every even length string need not contain even number of A's and even number of B's. Try to understand this point. Again, if the string is going to be, look at this, if the string is going to be containing even number of A's and even number of B's, then definitely the string is even length, but then all the even length strings need not contain even number of A's and even number of B's. This is the counter example. So the DFA for the even length string is definitely not going to do. Okay, so let's see how we can do it. So how can we classify this language? Now let us see the language. The language is going to be epsilon, because 0 number of A's and 0 number of B's, which is even number of A's and even number of B's, and then it can contain AA because even number of A's, or it can contain BB or it can contain combination of this A, B, B, A, B, A, B, B, A, B, 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 so on, so on. Finite or infinite? Definitely infinite. So if the language is infinite, we are not sure whether we will be able to give finite automata or not. But then let's try this. So before trying it, I would like to classify all these strings. See, always the number of states in a minimal DFA depends on number of ways or number of groups you can form depending on the question. Which means if you take all the strings possible over A comma B, according to the question, how many groups can you put them into? I think you can write it like this: number of A's in W and number of B's in W, right? So if you see this, number of A's in W and number of B's in W can be both even, which means they can be 0 A's, 0 B's, or 0 A's, 2 B's, 0 like that, a combination. And number of B's can be 0 like this, even, odd, even, odd. Try to understand this. So I can classify entire all these strings possible into all these classifications. Maybe I can give you one example. What is this string that will fall in EE, even category? Epsilon. Why? 0 number of A's, 0 number of B's. Or even AA. Why? Even number of A's and 0 number of B's, which is even. Or BB. Why? Even number of A's and then even number of B's. What about this? Even number of A's and odd number of B's. Even number of A's is AA and odd number of B's. So any string like this will fall here. What about this? Odd number of A's and even number of B's, right? What about this? Odd number of A's, odd number of B's. You can take any string possible and you can place them in one of these states. So therefore I will have one state representing this, one state representing this, one state representing this, and one state representing this. So we found out that at least there should be 4 states to distinguish the entire language into 4 classes. So let us say the 4 states are this. The 4 states are this: even state, even odd state, odd even state, odd state. The first one is going to talk about zeros and the second one is going to talk about ones. Zeros, ones. A's, B's. Number of A's, number of B's, number of A's, number of B's. Okay, so what we wanted is number of A's should be even and number of B's should be even. Therefore this state has to be final. So how did I reach this state? So how to analyze such a problem is, once you have got all these states and then when you are filling the transitions, it is better to take an example which will lead to some state. From there continue the problem. Just see this example, it will be easy. Now let us say you are in this state EE. How did you reach this state? Not without seeing anything, which means you can even say just by seeing epsilon, right? And if I see small a in this state, so what is the string that you have seen till now? Just small a. Now think about small a. How does it look like? It is looking like odd number of A's and even number of B's. Why? Because 1 A and 0 B's, which means on seeing small a, I'll go to odd number of A's and even number of B's. Fine. We have filled upon what happens on A. Now let us say I have seen B. If I see B from the initial state, what does it mean? It means that number of A's are 0, which means even, and number of B's are odd, which means even odd state. So if I see B, it is going to be even odd state. Okay. Now this state is complete. Why? We have shown what happens on A and B. Now take some other state. Let us say I am taking this state 0E. So in order to analyze what happens on small a and small b, you have to first know how did you reach this state. We have reached this state upon looking at small a, right? And now if you see one more a, what happens? it is nothing but even number of A's and odd number of B's. Sorry, even number of A's and even number of B's by 2 A's and 0 B's. Therefore, on looking at small a, it is going to be even number of A's and even number of B's. Now, again, how did you reach this state? By looking at small a, and if you get one more B in this state, by seeing small a, you are in this state. I don't know where to go on B, so let's check it. So if I get A followed by B, it is nothing but odd number of A's and odd number of B's. Therefore, on B, I'll be going here, right? So this state is also complete. This state is complete. This state is complete, because we are discussed on what happens on A and B and what happens on A and B. Now let us talk about this state. Okay, even odd. How did you reach this state? This state we have reached by seeing B, by even number of A's and odd number of B's. That is why we are in this state. If I see a in that state, it is going to make BA, which is nothing but odd number of A's and odd number of B's. Therefore, on seeing A, I am going to go to this state. Fine. Now let us see what happens for this state if it sees a B. How did you reach this state? By seeing small b. And if I see one more B, it is nothing but even number of A's and even number of B's. Therefore, on seeing B, I'll be coming to this state. Okay, fine. And now, this state is complete, this state is complete, this state is complete. Now let us talk about this state, 0, 0, odd, odd. So how did you reach this state? On seeing A followed by a B, or seeing B followed by a. Let us say, on seeing A followed by a B, you are here. If I see one more A, it is nothing but even number of A's and odd number of B's. If I see one more A, it is nothing but even number of A's and odd number of B's. Even number of A's and odd number of B's. Now again, how did I reach this one? By seeing BA, I reached this state. If I see one more B, it is nothing but odd number of A's and even number of B's. Understood? That is one method to construct the answer for this question. This is just one method.